Awesome. Hello, again, my name is Tyler Farr. I'm a rising fourth-year student at Georgia Tech, and today on behalf of my team at Georgia Tech, I'd like to discuss our characterization of water vapor transport through packed beds of Lunar Highland and Lunar Mare simulants. So the motivation for the study is we wanted to further develop technology for in-situ resource utilization on the moon, which is valuable if we ever want to establish permanent research stations or lunar ports. We also want to further our understanding of solar thermal water transport, extraction, and from permanently shadowed regions with a focus on characterization at ultra-low temperatures and pressures. This is also a continuation on the study of JSU-1A with the Lunar Mare and Lunar Highland simulants provided by XLF Labs. So now I want to go over some of the gas transport theory relevant to the microchannel flows in porous media. The three modes of diffusion being surface diffusion, Knudsen diffusion, and advective diffusion. The predominant mode of diffusion often depends on the flow regime that the gas is experiencing, and this is categorized by the Knudsen number, which is a ratio of the mean free path of the gas to the average particle flow diameter in the packed bed. It starts off with the continuum or slip regime, which we experience at low Knudsen values and high pressures, which is what we're experiencing here in this room, relevant to ISRU applications. The other end of the spectrum is a Knudsen regime at high Knudsen values or low pressures, which is more relevant to surface science. And in the middle, we see this transition between the two. The primary difference between the different regimes is that in the continuum or slip regime, you see a lot of particle-to-particle interactions, while in the Knudsen regime, you see more particle-to-wall interactions as there are less gas in there. Moving on to the experimental setup that we used, here we have the schematic of the apparatus. We introduced water vapor through a controlled evaporative mixer, which introduces 0.05 to 2 grams per hour of water vapor into a heated chamber to try to mitigate condensation issues with some embedded thermocouples. This then passes over a loosely poured packed bed of lunar simulants fit in between two mesh screens before being pulled out with a vacuum pump with the pressure at the inlet and outlet measured continuously. The packed bed of the simulant is either JSU-1A to validate with previous experiments, Lunar Mare or Lunar Highland simulants shown with optical imaging down here at the left. The main difference between these simulants is their average particle size and the circularity of these particles. As you can see, they look drastically different. The average particle size for the Lunar Mare showed to be the smallest, Lunar Highland the largest of the two, while JSU-1A fit right in between them. And this has a significant impact on the tortuosity or the gas flow path as it moves through the packed bed. Now into some of the experimental results. On the left here, we could see the pressure differential across the packed beds for the Lunar Mare and the Lunar Highland simulants for two different packed beds, which are characterized by the porosity or a ratio of their relative density or the bulk density over the specific particle density for the simulants. And each packed bed was run twice to rule out any effects of hysteresis. And as expected, we see a larger pressure differential across the Lunar Mare, given that it's the smaller particle size. Taking this data with the temperature and mass flow rate, we can plot out the total diffusivity or the bulk diffusivity for the different simulants. And again, we see the same trend where we have less diffusion through the Lunar Mare due to the smaller particle sizes. Of note is the sudden discontinuity in the total diffusion for the Lunar Mare, and that was due to what we believe is condensation issues at the higher flow rates and pressures for that part of the experiment. So what we wanted to do on the purpose of this study is to develop a model that would be able to predict the diffusivity through the entire spectrum of flow regimes and the different diffusion mechanisms. So what we did was we developed a piecewise model that takes both the total or bulk diffusion at the lower Knudsen values as well as the Knudsen diffusion at the higher Knudsen values. And in order to fit that model through the transition regime, we used model fitting with the experimental data at a few key parameters. These being the Knudsen transition value between the two different modes, the tortuosity shape factor, and the permeability shape factor, which is used in the Klinkenberg modified permeability of the gas flow. So taking this, we can then plot the total diffusivity normalized by the Knudsen diffusivity, which we see here on the right, with the solid black line being our model fit average for all 4 experiments per each simulant. The red dashed line being the total or the Knudsen transition value, while the tortuosity and unmodified permeability are plotted below, where again, we notice a trend where with lower particle average size, there is higher tortuosity and lower permeability through the packed bed. And of note is that we actually have witnessed a direct linear relationship with the permeability of the packed bed and the particle size that agrees very well with previous studies on JSC1A. So in conclusion, as I'm speaking a lot faster than I intended, this study was used to characterize the diffusion of water transport through packed beds of lunar Mare and lunar Highland simulants at conditions relevant to in-situ resource utilization. We developed a piecewise model that was computationally fit to experimental data in the relevant flow regimes. This model, the importance of it too, is also agnostic to the gas flow being used or the packed bed, meaning that we could apply this to various other volatile extraction systems or different regular simulants in further studies. And we hope that this study will inform further experiments on the thermal extraction of volatiles from lunar simulants using solar irradiation. I'd also like to thank the Reveals team and Survey for their help, contribution, and support through all this, whose work otherwise couldn't have been done. And with my rendition of a lunar, I'd like to thank you.